Okay, so a buffer is a solution that is actually a mixture of the conjugate acid base pair. And what that means is there is some of both. So there is some of the acid and its conjugate. So when you add a acid or base to the buffer, then the pH is going to change very little. So what it maintains nearly a constant pH to a point, and by relieving the stress on the equilibrium. So again, we're going to look at this as an application of Le Chatelier's principle. So when you have a buffer, then you can use this Henderson-Hasselbalch equation, but only for buffers. I'm going to spell buffer right here. But only for buffers. So then you have you have two forms depending on whether you have an acid or a base. And again, the best quantitative way to figure out if you have an acid or base, you're given Ka for acid and Kb for base. So these substances are weak. In the note about strength, it talked about that the conjugate pair of a very strong acid or base is useless as a proton donor or acceptor. So then if you want the buffer to be able to take care of stresses, then you don't want to have a conjugate that's not going to do anything. You need a conjugate acid to take care of basic stresses. If you have an acidic stress, then you need the basic side. If you do forget what pKa and pKb are, if you want to write that down, negative log Ka and negative log Kb. Okay? One other thing too, if you are not familiar with logs, some calculators automatically, as soon as you push log, they make a bracket. But those of you that took functions will know that there are, dividing here makes a big difference in a log law. So you want to make sure that you divide first. So you're dividing the anion concentration over the acid concentration and the cation concentration over the base. And where does that come from? So remember, when you have a weak acid, its conjugate pair is an anion, because an acid is a donor, a proton donor. And then when you have a weak base, which is a proton acceptor, then you get a cation because it's gained a positive as its conjugate acid. So that's why they're using the term here, cation and anion. You could substitute, if you like, that the anion is the conjugate base and the cation is the conjugate acid. That's fine. Okay, so we're going to do 3 different types of examples. We have this example 1. We're just going to calculate the pH of a buffer solution using the Henderson-Hasselbalch equation. And then example 2 and example 3, we're actually going to calculate the change in pH. So now we're going to look at what happens when there is a stress. Okay, so this example 1 is straightforward. So first of all, again, the Ka value you have to be given or is reference. So we have the pH of a 0.25 molar formic acid formate buffer solution. So this colon here is called buffer notation. And what it means is you have 0.25 molar of the acid side and its conjugate base side. You actually have both. So then you can use the Henderson-Hasselbalch equation. So again, an anion is negative, there's the anion side. But when you have buffer notation like this, they're both 0.25 molar, so their concentration happens to be equal. Now, it doesn't have to be perfectly equal. Usually it is, or usually they're pretty close. Okay, so we are given Ka, but not pKa, so that's an important first step. So again, pKa is negative log Ka, so negative log of 1.8 times 10 to the negative 4. Gives you 3.74, and then, excuse me, now we're ready to go. pKa plus log anion over acid. And again, when in the buffer notation, actually we don't need units for pH. When it's written like with that semicolon and a number out front, it applies to both the conjugate and the acid or base. And those of you that have taken functions, for example, will know that the log, if you do 0.25 divided by 0.25, that gives you 1, and the log of 1 is 0. So we're going to get 3.74. Okay, so that's a straightforward question, no stress or anything like that. When in the next question, now we're finding the change in pH and we're adding a stress. And our stress here is hydrochloric acid. So could you add a weak acid or base stress? Yes, but that would make the math, again, much more difficult. So for your first introduction to buffers, we're just going to consider strong acid and strong base stresses, because then they 100% associate, so that makes your life a little bit easier. Okay, so now we have, when you have a question like this, what you're going to do is you're going to do a before stress and an after. So change in pH, like when you do, right, the change in anything, then you always have to do like a pH 2 minus pH 1, pH initial minus pH final. So that's what we're going to do. So we're going to calculate the pH before we add any acid, sorry. So you can call it final, you can call it initial. So before adding acid. So again, we need pKa. Okay, and then we can do, should write it down right, sorry. Okay, so again, now we've got buffer notation here with 0.1, which means there is 0.1 of each. Okay, so then we are going to add a stress. Okay, so a couple of things if you want to make notes for yourself, maybe choose a different color. I'll choose blue. Okay, so we're going to, like I said, only strong acid-base stresses. So because we want 100% dissociation. So in our case here, we have HCl makes H plus and Cl minus, and we want concentration. So in this question, I happen to give you volume and moles. It doesn't have to be like that. So it could just give you concentration, but I'm just trying to show you all the possibilities. And then this should be liters. So divide by 1,000. Okay, so the reason we need 100% dissociation is if this is 0.01 molar, we want to know what this is, 0.01 molar. And again, the Cl minus we don't care about is a spectator ion. It is not a legitimate conjugate base. So that's another part to the 100% dissociation here. Then we don't have to consider the Cl minus at all. So if it was a weak substance and the conjugate, whether it was an acid or base, was a legitimate proton donor or acceptor, then that would really complicate the math. Okay, so we're just going to keep it simple here and use strong acid and strong base stresses only. Okay, so because it dissociates 100%, that means that the HCl is, of course, a source of H plus, or it increases the concentration of H plus. And so that's going to be important for when we do our ICE table. So once you start adding a stress to your buffer, then you need to consider how the equilibrium is going to handle that buffer. And why do I have to do equilibrium? Because this is a weak substance. And again, you'll remember from the other lesson that when something's weak, you have to do ice. So, with my blue. Actually, I'm going to write it right by the K because that's the best way to tell, okay? The most quantitative way to tell. Oops, sorry. Okay, so it's a weak acid. So when you have a buffer and we can use the Henderson-Hasselbalch equation, we can actually sort of cheat a little bit at ice. You could do these questions full out, Ka, products over reactants, ice, the whole 9 yards, but you don't have to. Okay, so we have 0.1 molar and we don't care about the water. And really, when we do the Henderson-Hasselbalch equation, we need the acid and the anion or its conjugate base. That's all we need. So I'm not going to fill in much more about that. So I'm going to call it modified ice. If you're going to use the Henderson-Hasselbalch, okay? Sorry for that wacky font, but it'll stand out, I guess. Okay, so now we have added HCl, which is a source of H+. So here you can see on the product side, we have some H here. So that means that you're increasing the concentration of something on the product side. So if you increase a product, what does the system do? It shifts left to use it up. which is fine. But then let's apply it to this situation here. So normally what we would do is we would figure out what X is because we don't know how much it's changing by, or maybe this is just a concentration or a qualitative Le Chatelier question and you don't actually have to calculate how much it's changing by. But in this case, we do know how much we want to change it by. So that's the thing with the buffer. We know how much we need to use up. How much H plus do we need to use up? Well, we need to use up this much. Okay, and again, it doesn't really matter what the H3O started with or what it's going to end up with, because all we care about is the acid and the anion when we are doing the Henderson-Hasselbalch equation. Okay, so if it shifts to the left to consume the added H3O plus, that means that the concentration of the acid is going to increase by 0.01, and the concentration of its conjugate base is going to decrease by 0.01. Okay, so as a result of the shift left, then the reactant is going to decrease and the product is going to decrease. So 0.1 plus 0.1 is 0.11. 0.1 minus 0.1 is 0.09. Excuse me. And now we are ready to go back and do the Henderson-Hasselbalch. Now we have the same pKa, and we have the anion concentration, and we have the cation concentration. So now they're no longer the same because it had to shift. So we started at, so usually we do final minus initial, right? Okay, so we started at 4.74, we ended up at 4.65, and that is a pH change of down, or more acidic, 0.09 units. So not a very large change in pH at all. So this buffer capacity was perfectly fine. And again, if you continue in chemistry, you'll look at a way to calculate buffer capacity. But here we're just looking at whenever it says to do the change in pH, then you have to do a before and an after, or a final and an initial. And you have to look at a stress. So it's sort of 50-50. You either have a weak acid or a weak base buffer, and you're either adding a strong acid or a strong base as the stress. Okay? So let's do a basic one. What is the change in pH when 5 times 10 to the negative 3 moles of HCl is added to 75 milliliters of 0.2 molar ammonium buffer? And then we're given the Kb value this time. So again, there it tells you this is a base in case you forgot that ammonia was a base. So we can go ahead, calculate Kb, pretty straightforward. Oops, I forgot the negative log, sorry. They happen to have the same Ka and Kb values, so we get the same pKb. And then before, no acid yet. So all we're considering is the base. So now when you have a basic buffer, then you have to use the basic form of the Henderson-Hasselbalch equation. And again, the cation being this positive here with the conjugate. if you did homework from the last section, you would have noticed that whenever you have a base, there's always this extra step because we don't deal with pOH. There's no pOH scale. So you want to make sure that you change the pOH into pH easily using this formula. Which you might say, isn't that a little bit redundant? But you really have to make sure, you know, that you're following proper form, really. If you're running out of room, you can write at the side. There's lots of space here now. Okay, so maybe I'll do that. So after is going to be adding acid. And you can go right into calculating concentration. So again, this time I gave you moles and volume for whatever reason. It is not always, it doesn't have to be like that. And again, we want this to be in liters because it's moles per liter, right, for concentration. Okay, so this is 0.067 is the amount of hydrogen that our buffer needs to take care of. So we need to write our modified ice table. So bases are acceptors. And the good news is with buffers, you're given this, right? You're given the buffer notation. So it tells you the formula for the base, and it also tells you the formula or acid and the conjugate. So that can help you. You just have to remember what's left over. Okay, so initially we have 0.2, 0.2. So this time we have base and cation. But now we have a problem here. So in this case here, this was more like common ion, right? It was a source of H+, we had H+, we knew exactly where to put it. But down here, now we're still doing H+, but now there is no H+ in our equilibrium expression. So there are two ways to think about this. If you have if you add an acid to a base, what starts to happen? Well, they start to neutralize. And what does that mean? What do you make when you neutralize something? If you put H with OH, a positive and a negative together, you're going to get a compound. That's what chemistry is. Opposites attract. So what is HOH? Oh, that's water. So there is water in this equilibrium expression here. So you can think of it as the water starts to increase, which is here, this water here. So you're increasing now a reactant, which means it needs to shift to the right to consume it. Or you could actually think of it like the OH is going to decrease. So if the hydroxide decreases, then it's still going to shift to the right to make more. And both of those are equivalent. It doesn't matter what you think of. And really, again, because we're doing the Henderson-Hasselbalch equation, we don't need concentrations for water. We don't need concentrations for hydroxide. We just need the base and its conjugate acid or the cation. Okay, so I'm going to write all that down. Oops. Okay, and again, how much does it shift right? Oh, we know how much we need to consume. Okay, so again, this value is our change value. How much does it need to change by? So now this time, the reactants are going down because maybe you're going to think of it like you increase the water, so shifts right, or because a product is decreasing, then it shifts right to make more. And to be honest, in a vessel, it's not like it tells us, hey, you know, this is what's happening, this is why it's shifting. So all we can do is use the chemistry concepts and apply them in both ways. Okay, so this is 0.267 and 0.133. And now we are ready to go back and do pOH. Making sure you do the 0.267 divided by 0.133. So if you have a calculator where you push log and then it automatically puts brackets, then that can actually be helpful here. But you don't have to, you can just do it in more than one step. No big deal. Or put in your own brackets if you want. Okay, so again, making sure, let's change that into pH. Okay, and then now we can do change in pH. pH final minus pH initial, or pH after minus pH before. And it actually, to be honest, doesn't really matter which order that you subtract them in. It just, so this one here, it went down. Why did it go down? Because we added an acid, and acids are lower in the pH scale, but that's not really relevant here. Okay, so it went down 0.3 units. That was a lot of base, 75 milliliters, but our buffer took care of it, so not too bad. Okay, so